Unit 1B, Lesson 3. This will align with 6.4, 6.5, and 12.2 in your textbooks. There's two standards we're going to discuss in this lesson. The first one, prove polynomial identities and use them to describe numerical relationships. One of the identities we're going to focus on is the Pythagorean triple identity. Second standard, know and apply the binomial theorem for the expansion of x plus y raised to the n in powers of x and y for a positive integer n, where x and y are any numbers, with coefficients determined, for example, by Pascal's triangle. All right, if you recall a few lessons back, I just introduced you to Pascal's triangle and the binomial theorem. Now we're going to refresh on that and use that to discuss this standard. Key vocabulary and things to refer to in this lesson: Pythagorean triple. A Pythagorean triple are three integers that satisfy the Pythagorean theorem. So if we can plug in three integers, it makes the Pythagorean theorem a squared plus b squared equals c squared true. Then those three integers form a Pythagorean triple. Talk about Pascal's triangle. We're going to use that for the coefficients of a binomial expansion, and the binomial theorem itself tells us how to expand a binomial. In the first standard, one of the identities we have to focus on is the Pythagorean triple, which states that x squared plus y squared, that quantity squared, is going to be equal to x squared minus y squared, that quantity squared, plus 2xy quantity squared. So we're going to go through and verify that this is true. We're going to do that by expanding the left side of the equation and then expanding the right side of the equation and simplifying and showing that both sides of the equation are actually equal to each other. So first we're going to work with the left side. If I have x squared plus y squared, that quantity squared, I'm taking that, multiplying by itself. So now we just have to use the FOIL method. X squared times x squared is x to the fourth. X squared times y squared is x squared y squared. Y squared times x squared is the same thing, x squared y squared. And then y squared times y squared is y to the fourth. Combining like terms, we have x to the fourth and plus 2x squared y squared plus y to the fourth. So if we take the left side of this equation and expand it, we end up with x to the fourth plus 2x squared y squared plus y to the fourth. Now we're going to work with the right side of the equation and show that it simplifies down to the exact same thing. Now if we work with the right side of the equation, we have x squared minus y squared quantity squared plus 2xy quantity squared. So we can simplify, expand this out. Again, we're going to have to use the FOIL method. And then we have plus 2xy quantity squared. So if we FOIL this out, this should have been x squared. We have x squared times x squared, x to the fourth, x squared minus y squared, or x squared times a negative y squared is going to be minus x squared y squared. Then we have a negative y squared times a positive x squared. So again, we have minus x squared y squared. Negative y squared times negative y squared is a positive y to the fourth. And now, if we multiply this out, we just have to distribute this 2 to all of these factors on the inside. So we'll have plus 2 squared is 4, x squared y squared. Now we combine like terms. We have x to the fourth. A negative x squared y squared and a negative x squared y squared makes a negative 2x squared y squared. But then we have to add a positive 4x squared y squared. So we end up with 2x squared y squared and plus y to the fourth at the end. So now if we look, what we end up with on the left side of the equation and what we end up with on the right side of the equation, if we expand those out, we have the exact same value expressions on each side. So that means this Pythagorean triple identity does hold true. As long as we put in positive integer values for x and y, this is going to be true. We're adding, subtracting, and multiplying integers so our results are going to be integers. So quickly go through an example showing that this does hold true. You can try this afterwards on your own, see if you can come up with a combination of two positive integers that will make this not hold true. Okay? So for an x value, let's just say I'll pick 1, and for my y value, I'll pick 3. Now if I plug these in the first part, 1 squared is going to be 1, plus 3 squared is 9, and then we have that whole quantity squared, equal to, over here 1 squared again is 1, minus 3 squared would be 9, that quantity squared, we'll fix that quick, quantity squared, plus inside the parentheses we have 2 times 1, which is 2, 2 times 3 is 6 squared. Now if we simplify these, 1 plus 9, we get 10 squared, equal to 1 minus 9 is negative 8, that quantity squared, plus 6 squared. Again, simplifying all these out, we have 10 squared, which is 100, equal to negative 8 squared is 64, plus 6 squared is 36, and the last step, 100, equal to 64 plus 36 is 100. Okay, so we came up with values for x and y that when we simplify out, make the Pythagorean theorem true. A squared plus b squared is equal to c squared. If we're talking about a triangle, which is what we're referring to when we use the Pythagorean theorem, we say we can't have negative values, and if we notice we have a negative 8 here, that would just be saying taking into consideration the direction. If we're talking about a right triangle on the coordinate plane, if this was referring to our x value, our x-axis, we would be going to the left on our coordinate plane. Okay, so if you want to go through, try a few combinations on your own, seeing if they work and hold true. As long as we come up with 3 integers that make the Pythagorean theorem true, that's called a Pythagorean triple. 2 more identities we are going to discuss: the sum and difference of cubes. If we have a cubed plus b cubed, that's equal to a plus b times the quantity a squared minus ab plus b squared. If we have a cubed minus b cubed, that's equal to a minus b times the quantity a squared plus ab plus b squared. So if we have a sum of cubes, we're adding, in our first set of parentheses we're adding, and we're subtracting in the middle. If we're subtracting a difference of cubes, in our first quantity parentheses we're subtracting, and everything is addition that follows. In this next portion we're going to factor each sum or difference of cubes. First problem, we have w cubed plus 8. We need to first rewrite this so that we can see what both cubes are. This is the same as w cubed plus 8 is the same as 2 cubed. Now we can see what our a value and our b value are. So all we need to do at this point is follow the pattern. In our parentheses, we have w plus 2 times, in parentheses over here, going to be w squared minus w times 2 plus 2 squared. Only thing we need to do now is simplify a little bit. W plus 2 times the quantity w squared minus 2w plus 4. So first we have to rewrite 8 to see what both of our cubes are, and then just follow the pattern. In this next example, we have 27x cubed minus 64. The first thing we need to do is rewrite these so we can see what our a and b values are. So we can rewrite 27x cubed as 3x quantity cubed minus 4 cubed. So now we can easily see what our a value is, 3x, and our b value, 4. So we follow the pattern. 3x minus 4 times the quantity, and we can use a bracket again because we're going to have more parentheses. So we have 3x quantity squared plus 3x times 4 and then plus 4 squared at the end. And last step, we just need to simplify this. So we have our 3x minus 4 times the quantity. 3x squared is 9x squared. 3x times 4 plus 12x and then plus 16. So using the sum or difference of cubes, rewriting each term so we can identify what our a and b values are, and then use the pattern. Now we're going to get to Pascal's triangle and the binomial theorem. Remember Pascal's triangle, this is row 0, row 1, row 2, row 3, and so on. We start and end each row with a 1. How we come up with the numbers in the middle, if I take 1 plus 2, I get 3. 3 plus 3 is 6. 4 plus 6, 10. 5 plus 10, 15, and so on and so forth. So you take the two numbers above, add them to get the number below. And then we have the binomial theorem. So if we have a plus b raised to some power where n is a positive integer, we can use the binomial theorem. That shows us how to expand that binomial. This looks really confusing, this summation. It's actually a lot more simple than one would think. Okay, so we'll go through a couple examples. You can see how to use the binomial theorem and Pascal's triangle to expand a binomial. Use Pascal's triangle and the binomial theorem to expand each of the following. The first binomial we have, a simple one, x plus y raised to the fourth. First, what the 4 for our exponent means, we're going to go to the fourth row of Pascal's triangle. So if you look at Pascal's triangle, you go to the fourth row, we're going to take those numbers, which are 1, 4, 6, 4, and 1. These are going to be the coefficients in front of each of our terms when we expand this binomial out. So if I start to expand this out, my first coefficient is going to be a 1 times my first value is x. That is going to start to the fourth power times y to the 0 power. Okay, so I have my coefficient. This portion is our binomial theorem. My first term raised to the highest exponent it can be times the other term, our other variable, raised to the lowest exponent. If I take these two exponents and add them together, they always have to equal what we start with. And then I'm going to add to this, my second coefficient is 4 times x. The exponent value on my x variable is going to decrease by 1 each time. So this is going to be 3 times y to the first power. That's going to increase by 1. 3 plus 1 gets me 4. Plus 6 times x squared times y squared. Plus 4 times x to the first y cubed. And then at the end, plus 1 times x to the 0 times y to the fourth. So we use Pascal's triangle to find the coefficients in front of each of our terms. We start with our a value, which was x in this case, raised to the highest exponent. That's going to decrease by 1 each time. And then the exponent on y is going to start at 0, and that's going to increase by 1 each time. That's the binomial theorem. All we have to do now is simplify each of these. Anything raised to the 0 power is 1. So our first term is x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed, and then plus y to the fourth. That's how to use Pascal's triangle and the binomial theorem to expand a binomial. In the last example, we want to expand using Pascal's triangle and the binomial theorem 2x minus 5 quantity squared. What I'm going to do first is change this binomial to addition. This is the same as 2x plus -5 quantity cubed. Alright. Coefficients, now if we go to Pascal's triangle, we have to go to row 3. So we know our coefficients are going to be 1, 3, 3, and 1. Go through the same process we went through last time. 1 times 2x quantity cubed times -5 to the 0 power plus 3 times 2x to the second power times -5 to the first power plus 3 times 2x to the first power times -5 to the second power, and then the last one plus 1 times 2x to the 0 power times -5 to the third power. Again, if you look, if I add these exponents, 3 plus 0 is 3, 2 plus 1 is 3, 1 plus 2, 3, 0 plus 3 is 3. The exponent on 2x is going to decrease by 1 each time. The exponent on -5 is going to increase by 1 each time. All we have to do at this point is simplify. -5 to 0 power is 1, so we have 2x quantity cubed, which is going to get us 8x cubed. The next part, we have -5 times 3, which is -15. 2 squared is 4. 4 times -15 is -60 x squared. Next one, we have -5 squared, which is 25. 25 times 3 is 75. 75 times 2 is 150 times x. And the last one, we have -5 cubed. 5 times -5 is 25. 25 times -5 is minus 125. This is how to expand a binomial using Pascal's triangle and the binomial theorem. Notice if this sign is negative, that our signs are going to alternate at the end. We go from positive to negative to positive to negative. In this lesson, we went through a lot of information. First, we went through some polynomial identities. We showed why the Pythagorean triple identity works as long as we're filling in positive integers. Then we also went through Pascal's triangle and the binomial theorem and went through how to use those to expand binomials.